So, welcome. My name is James Wormold. I'm a writer here at Europa Science, publisher of Electro-Optics. In this web panel, we'll be discussing how photonics is transforming environmental monitoring and the challenges and opportunities that comes with it. From tracking greenhouse gases in the atmosphere to detecting pollutants in our rivers and lakes and analyzing air quality in real time, photonics-based sensing systems are providing unparalleled accuracy and insight. But although these applications can make a big impact, there are also some big questions to answer. Questions like how to implement photonic systems to get the best results, what differences need to be taken into account to monitor various elements, and how do we ensure the recorded data is accurate? In today's session, our expert panel will answer these questions and more. They'll dig into the latest innovations in the use of photonics for environmental monitoring, share practical strategies for overcoming deployment hurdles, and discuss the opportunities for collaboration that can push the vital field forward. Joining us to share their knowledge and expertise are Liam O'Phelan, Project Coordinator at the Passepartout project at Munster Technological University, where he leads the nanophotonics group. Dr. Dave Nelson, President of Aerodyne Research and leading figure in molecular spectroscopy and environmental gas detection. And David Blair, who's the Chief Product Officer at Headwall Group, and he brings his expertise in hyperspectral imaging systems and their practical applications. Welcome, gentlemen.
Thank you.
So before we jump in, I should point out that the discussion will be available to watch on demand alongside the others in the Electro-Optics series in the webcast section of the website for 12 months after today, in case you'd like to recap on any of the information. But back to today's discussion, I'll kick things off by putting some questions to our speakers to converse on. But I'd also love to hear from you, the audience. So if you have a question for any or all of our guests at any point, please use Zoom's Q&A tab in the More section maybe to send them in. No topics too niche. And if you're watching on demand, you can still send the questions over to us anyway, and we'll make sure they get passed on. So I can see our panelists here are ready and raring to go after all that waffle. So let's get started with the questions. So I've already mentioned some of the benefits of environmental monitoring, such as data, insight and analysis, all combining to enable best practice sustainability. But we all know about those. Well, let's talk about some of the common challenges that can arise when implementing photonic systems to gather the data. Maybe Liam, if you could start with your experience on Passepartout with the challenges.
So yeah, as you say, the photonic systems are have the advantage of being very highly specific, suffer from some low interference with other compounds, and can operate with low calibration. The bad part is they're generally quite expensive, and there's quite a number of pollutants now, number that have a high spatial and temporal variability, and I see quite a big need for sensor networks that are higher density sensor networks, higher numbers of sensors per square kilometer and similar, which means that the cost needs to come down for this to happen. So some of the big challenges is how these laser gas analyzers are put together, very often needing a skilled engineer to align each mirror, each lens, each component. So so I think we need to move on from that and find newer ways of putting together our optical gas, our photonic-based gas analyzers to drive down costs by significantly.
Okay, thanks, Liam. And Dave, what about the problems that you faced at Aerodyne? Are they kind of similar, or have you any different ones?
Well, I certainly agree with those comments. I was going to answer in a slightly different way. So a general challenge of field measurements, you're not in a laboratory environment typically. And so a lot of optical instruments, maybe not all, but a lot of them have thermal dependencies on their calibration. And so temperature stabilization can be a serious challenge for many instruments, or if you can't stabilize it, adapting, being able to understand the calibration as a function of temperature is really important. For larger instruments, this can also couple with power requirements in the field. So a lot of our instruments, for example, are extractive gas sampling instruments where you need to establish a gas flow, usually with a vacuum pump. And so that can require significant electrical power, which is also a constraint in field measurements. It can constrain where you're able to work if you require a power line. And then that can couple back into the thermal problems because if you're consuming a lot of power, you're going to dissipate a lot of heat. Then you need maybe more air conditioning. Then you need generators. And so depending on the design of the field site, all of these environmental factors can become important. And then in addition, we do a lot of mobile measurements, either driving around in a vehicle or flying on an aircraft. And in mobile operations, the additional challenges are obvious. You've got, vibration, you've got G-forces. The data interpretation requires that you know exactly where you are all of the time. And so those are the sorts of challenges that we've encountered in the kind of environmental monitoring that we typically do.
Okay, thank you. And what about when using hyperspectral imaging, specifically, David? What are the challenges there with those kind of tools?
Yeah, certainly. I think that hyperspectral has certainly some common challenges with other technologies and some unique ones as we think about the way that the environment you're collecting in changes from the lab out into this more robust remote sensing world. Your background is diverse and your ability to control that background is limited. Solar angles, cloud, humidity, all of these basic parameters of our environment actually influence our ability to measure and to get consistent results. That is compounded by the fact that the background here in Boston in the United States is different than the background in Cambridge in the UK or in Nanjing in China. Each area has different geological background features, atmospheric background features, and all of that needs to be addressed and considered when collecting and producing repeatable data. Of a similar vein is also, as you think about that data itself, we're moving from a world where you have simple point lab measurements to wide area collection. Data management is a huge piece of what the industry is working through and needs to resolve in order for the photonics-based sensors to really propagate heavily in the market. There's been a natural tendency to save all of the data and to work with it over time. But these are very large data sets as you're now interrogating the entire scene. So the ability to reduce the data, to reduce the dimensionality of the data you choose to keep, and to store answers rather than raw data is a critical piece as well.
Okay, thank you all. And some of those challenges mentioned were kind of based on specific location that's being monitored, and the conditions that there are in that location. We talk about environmental monitoring, but the environment's made up of multiple different elements, of course. What are the differences between using photonics to monitor our air compared to monitoring water or Earth, for example? Maybe Dave, if you could start us off there, please.
Sure. So for most optical techniques, air is the friendliest environment. That's where electromagnetic waves freely propagate. And for some applications, air and water are equally attractive. Soil's generally difficult. For our work using high-resolution lasers, we have to make the final measurement in air at reduced pressure. But we've developed a lot of methods to extract the molecules that we're interested in, either from the liquid phase or from soil gases. And so that's the approach that we've been using is the final measurement is going to be made in air, but we can still probe liquids and soils using clever techniques. And for example, some of those techniques are to bury diffusive probes in the soil at different depths. And if you let them sit there for a couple of minutes, they will come into equilibrium with the soil gases. And so then you'll have a plug of gas within the probe that you'd like to measure. And with clever gas transfer techniques, you can push that plug of gas into the instrument, capture just the right timing so that you get the plug of gas that has the soil gases, and then interrogate it and learn the chemical composition, even the isotopic composition of the soil gases at remote locations.
Right. And Liam, with the Passepartout project, what kind of elements do you monitor there? And what kind of techniques have you developed for doing each of them?
For Passepartout, we were looking at pollutants in urban areas, black carbon, NOx, ozone, carbon monoxide, and some of the greenhouse gases. So all in the gas phase. So yes, gas phase is a relatively benign environment to make measurements in. The absorption cross section is low, so you need long paths or various or tricks. So in Passepartout, a lot of the techniques were based on photothermal and photoacoustic spectroscopy, which were allowed to allow miniaturization of the sensor. When working in liquids, obviously well, completely different challenge, where the absorption tends to be much stronger. You can very often have a water background. Techniques like Raman spectroscopy are quite popular. Mid-infrared spectroscopy can also be used where you can overcome the water absorption, say using techniques such as attenuated total reflection spectroscopy, and others basically deal with the fact that you or try to avoid having to pass through your sample, or if you can work with the Venison wave and so on to interactor sample. Similar challenges for solids, where you also have very strong absorption and a not perfectly homogeneous material.
Right, and so from some of those different techniques, maybe David, if you could tell us about how the kind of hyperspectral imaging components that you put together, that you develop, how they're best suited to monitor those different types.
Certainly, I think, hyperspectral really as a surface reflectance spectroscopy technique really finds that soil and typical solid measurements are the most effective areas for environmental monitoring. We find that while they may be heterogeneous, they are relatively static, unlike aerosol-based samples, which are dynamic, where noise can often dominate over signal and the types of detection capabilities of those imagers. And so soil-based measurements typically are where we see most of our users and community embracing the technology. A growing area of research and interest is water-based monitoring measurement, where either we can work through surface-based materials, harmful algae blooms or similar surface level contaminants, or that even though there is a relatively mixed surface there, we can determine some chemical characteristics or precursors and evidence of other materials. Water itself, optically speaking, is a complex medium given its scattering, glint challenges when trying to collect and acquire data. So really, soil, geologic formations, and materials that are earthbound tend to be the best and most effective.
Okay, so I mean, if we dive deeper into the subject matter, if you'll excuse the pun, I'm going to direct this one at you, specifically Liam. You and your team on the Passepartout project have been overseeing the detection of fugitive methane emissions. Tell me about the photonics techniques you've been using specifically to do this. Tell me more about them.
Oh, yes. So some of the very popular techniques for fugitive methane detection are cavity ring down spectroscopy, infrared camera-based systems. We've been working on quartz-enhanced photoacoustic spectroscopy systems, or developing new versions. So as I mentioned, the challenge is the low absorption cross-section. So traditional techniques, you need a long path length, hence cavity ring down. Quartz-enhanced photoacoustic spectroscopy uses a quartz tuning fork as the transducer, which allows you to pick up a very weak signal quite effectively, and it's relatively immune to background noise, which allows you to detect the detect the presence of methane while even using quite a small cell or quite a small photonic unit. So the future of methane detection market it's a big market. There's quite a huge demand for large number of units, which is why I'm always thinking about cost and cost reduction. And so techniques like QPAS are quite have very strong potential for miniaturization. So yeah, sorry, maybe scalability is probably the best word to use. That really thousands, tens of thousands of units can well be imagined, or more even. The other factor is a lot of the current approaches, you still need a skilled operator, and so I think we need to move away from the scenarios where you have a skilled operator looking for the fugitive methane and into situations where it can be done remotely, using continuous monitoring or whatever the case may be.
Okay. So tell me a bit more about the project, sort of in general. When did it start? How far along are you on the project and your kind of goals for it?
Yes, Passepartout ended at the end of last year. It was a Horizon Europe funded innovation action. The goal of Passepartout was to create mobile pollution monitors for urban pollutants and greenhouse gases. So bigger task was miniaturization. Cost reduction was is now being targeted in our next phase of projects.
Right. Yeah, you mentioned that being one of your sort of main challenges with the cost reduction and finding skilled engineers. Do you think there's a lot more that can be done in terms of raising the sort of skills gap to find the people to do that then?
So, let's say we've had a few, let's say some of our industrial partners make the complaint that it's quite hard to hire optical engineers for assembling of these quite precise laser gas analyzer based sensors. And indeed, they sometimes don't have enough work. Even if they were to hire one, sometimes the smaller companies don't have enough work to justify doing it. So it kind of creates quite a bottleneck. So again, the direction I see the well going is where you're dialing down the skills needed to assemble these. Something can be done more in an automated fashion, which then clears that particular bottleneck.
That's good. That's good. So I mean, moving on to Dave and your work at Aerodyne, then some of the work you oversee utilizes isotopes as environmental tracers. Tell me, what have you been able to learn from the use of the laser-based methods of those?
Yeah, so by way of background, isotope ratio mass spectrometry, IRMS, has been the standard for making isotopic measurements in the environment and in geochemistry for decades. But laser measurements have distinct advantages for some isotopic measurements, not all, but for some. And so the potential advantages of optical methods include lower capital costs. Laser systems are often much less expensive than mass spectrometric systems. Lower operating costs. So we were just talking about the need for a skilled operator. In general, IRMS, mass spec methods require a very skilled operator. And that's less the case for optical methods. They can be automated. Optical methods offer the promise of direct continuous measurements with little or no sample preparation. There's been many publications on that where people have made continuous isotopic measurements of the atmosphere for CO2, for methane, for other gases, for months on end, years on end, with very little sample preparation required. Optical methods can also have fewer interferences. They're not completely immune from interferences, but they often require less sample prep to remove interferences than mass spec does. Another advantage is a complete elimination of the isobar problem. So isotope ratio spec in general suffers from this isobar problem where when you're measuring carbon-13 CO2, you're also measuring oxygen-17 CO2. And there's no way to separate those two. You have to do a correction factor. And if you want to measure O17, it's virtually impossible with mass spec. because it's dwarfed by the C13 signal. Optical methods don't have that problem. It's based on a row vibrational spectrum, and all of the individual isotopal logs can be completely resolved. Another advantage of optical methods is the potential for field deployment, which is much more difficult and challenging with mass spectrometers, and the potential for rapid measurements. So there are several papers where people have done 10 hertz measurements of isotopic composition, which allows eddy covariance isoflux measurements in the environment. And then finally, another potentially huge advantage that hasn't been fully exploited, but is in the future going to be exploited, I believe, is that optical methods are in general non-destructive. And so this precious sample, if it is precious, can be recycled. That's really important in geological applications. There are some challenges that optical methods have that are different than mass spec, and some of those include matrix effects. So usually we're measuring the molecule of interest in a buffer gas, often just the atmosphere. But sometimes the composition of that buffer gas can change, and that can affect the optical signal. So you have to be aware of that and calibrate properly. Optical methods often have a concentration dependence where the isotopic abundance that you measure will differ depending on the concentration of the gas you're measuring. The isotopic composition isn't really varying. It's just that there is a calibration issue there that mass spec usually doesn't have to face. Instrumental drift needs to be dealt with. And in general, optical methods are doing a complex spectral analysis to retrieve the isotopic composition. And that's very different than mass spec, where they're just counting electrons. So that's an extra challenge. And the usual thing with many optical techniques, often you have a set of high reflectivity mirrors at the core of the instrument, and you need to keep them clean. And that's also a little different than mass spec. But in general, in summary, I think the opportunities are great for the places where optical methods can be applied.
Okay, so a lot of challenges there to work through, but also a lot of kind of benefits, offering a goal at the end of it. How are you kind of approaching some of those challenges, finding solutions to them then?
So things like instrumental drift, for example, that was one of the challenges. We've developed a technique which is basically stolen from IRMS, which is to switch between sample measurements and working reference measurements very rapidly. And so if every minute we take 30 seconds to measure an inexpensive but stable working reference, we can correct for drift in the instrument. The complex spectral analysis, that's another challenge. That's something we've been working on for ages, but it involves basically improving your algorithms and making sure you completely understand the spectroscopy. So these are solvable problems, and certainly don't want to give the wrong impression. I think in general, optical techniques for some measurements are almost completely supplanting IRMS. So for example, for water isotope measurements, that's all pretty much done optically now with cavity ring down spectroscopy. And for carbon dioxide isotopes, it's strongly going in that direction, especially for exotic isotopes of carbon dioxide like 17O-XS or clumped isotopes of CO2. The optical methods have tremendous advantages.
Okay, thanks, Dave. And so, David, from a customer-facing standpoint, then, what would you say are the most common environmental monitoring demands that users have, where hyperspectral imaging is used to meet them?
Yeah, Certainly, and I'm going to break this up, I think, into two sections here. One is really the needs and expectations of the equipment, and then really the markets and the applications where we're seeing this requirement. As we listen to our customers and understand their expectations, there is a strong expectation of precision and accuracy of the measurements, rooted in this historic capability in the lab environment to have controlled background, right? An element we talked about previously, an understanding of the sample, of the measurement, to have time to interrogate if necessary. And so there is this expectation and requirement from the user community to maintain as much of that as possible. It is rare that a single solution, any of the optical solution we're describing, it's rare that any one single solution solves all of a user's problems. So trying to find systems that are more interoperable. So thinking about how we generate our data, how we can share that data with other software platforms, with other hardware platforms, that's a need and an expectation that the users are looking for. There's a request and really a demand for accurate geopositioning of the data. Again, on the benchtop, you know where your sample is. If you are out on a UAV or on a manned aircraft or a satellite looking at the ground, and you want to take action with the data you have, knowing that something is within a 30-meter circle may not be an acceptable outcome. There's an expectation for centimeters of spatial accuracy, not meters of spatial accuracy, but still with an expectation of the price point of the GPS inside your cell phone, right? That there are some expectation management challenges that we go through there. And similarly, and I really want to, appreciate Liam's comment earlier about the need to drive down cost through these products, through volume. One of these other expectations and understandings is, especially in the optical imaging space, point measurements with photodiodes and other similar technologies, translating the cost of those detectors into imaging arrays is a very different form factor. It's a very different cost structure. And being able to standardize and bring together some type of volume capability, but also to really communicate that difference between a single pixel on scene and 4 megapixels on scene, right, or 50 megapixels on scene, depending on the camera. These are all things that we work through with the customers to understand what is the expectation, what's the requirement, what's the need as we go through these products together, because there is that expectation of precision, of accuracy, of wide area coverage, of the ability to have high temporal collections. Right? I talked in my opening statement about data management and this expectation and need to be able to reduce that data quickly, to process it efficiently, and to be able to remove the unnecessary data elements so that you don't run your own data storage warehouse in any of these optical systems. And I think the last piece comes down to it being repeatable. These are technologies that grew up in the research community, fundamental research to applied research, into early adopter use cases. There is an expectation that a user of the technology can push a limited number of buttons to run a predictable, expected workflow to generate a consistent data output. And that is, again, something that is a demand that we see routinely is I no longer want raw data that I play with. I want an answer and I want it the same way every time. And I think those are, they're important things that we as producers of these technologies need to be aware of and drive through, and certainly something that I think the broad hyperspectral community has heard and is working to address. These customers, when we look at where are they spending their time with the instruments, they're focused in agricultural measurement. It's the number one series of application-centric questions that we get. How can I measure soil conditions more accurately than basic vegetative indices, NDVI and similar? How can I understand advanced methods of plant health and vitality? Can I estimate yield at some point earlier in my growing season? Can I mitigate invasive species? Can I address die-off or disease early in my growing cycle or instantaneously as it matures and develops so that I can reduce my risk to my overall environment? In the water and water quality space, the algal bloom situation continues to amplify as we see waters warming, right, as a result of global warming. The need to be able to quickly identify materials so that they can be mitigated with a minimum amount of the chemicals and processes required, or to allow man-made, human intervention to mitigate that earlier is critical here. And also understanding not only the sediment in the water, but the origin sources. Once I have wide area capability, I can not only see that I have an inflow of sediment from a river, but now I can start to see what is the source of that and understand the infrastructure change, the land use change in real time, and better predict where will water flow, where will soil degrade, where might topsoil be unstable. And those are big areas for us. Another space that is growing as mining and geological survey companies look to improve their impact and footprint within the ecosystem, better understanding how exploration happens, how precursor minerals are identified, how the impacts of the environmental actions taken during mining play out, and how the area is mitigated afterwards. Those are all supported by wide area surveillance, optical imaging systems. And so that I think that there is a wide range. These are the ones we see the most, but it's wonderful to be in a space like this, because every day someone asks a new question we haven't thought of, and it's new possibilities.
That's a good point you make, yeah, and that kind of touches on what you were saying earlier about some of the challenges, but also about how to apply the technology for different purposes. And how important do you think is it for a kind of vendor to offer that kind of post-sale service to produce that kind of custom service to customers, and helping them kind of integrate the technology into their own system and situation?
So at this point, I think it's mandatory. And I'll speak heavily on the spectral systems, but I think this applies more broadly as well. That it is still an evolving capability. There is still a limited amount of standardization, right? Industries like and organizations like IEEE are working to standardize different data structures and formats to try to bring together companies and parts of the ecosystem that are not currently connected. But until we get to a point where either there are their own industries that exist as service providers, or the data continues to evolve and the processing pipelines evolve in a way that users are able to intervene themselves, I think it's a necessity for the end user to be successful and for the technology to propagate.
Right. And so moving on in terms of time now, I'll put another kind of open question to the group, but I'll start off with you, Liam, if that's okay. So one of the most important parts of monitoring and tracking environmental effects is accurate data management. How do teams from both sides of the fence, starting with you, Liam, in research and applications, ensure the data that they record is accurate?
Yes, but making sure that the instruments are properly calibrated obviously is a key point. Yep. Otherwise, there's big question marks over your data. Needless to say, there is. Let's say the level of standardization is probably not as the level of standardization is improving is probably the nicest way of saying it. And there's increasingly pretty much all modern research projects have a requirement to put in data management plans, have ways of making the data easy, interoperable, fair, and easily accessible. Some of that is, and there's also requirements to put data in open repositories. Using the metadata, as David was mentioning, it's very important that they locate all the supplementary information, where the measurement was taken, how it was taken, the experimental conditions. Very important that it's attached as metadata to the data set. And there's various standard formats for how spectroscopic data can be recorded. So there's increasing trends to have this done properly, which is very, very important.
Yeah, and then that speaks to what David was kind of saying about standardization as well. And Dave, would you agree with those kind of calibration kind of techniques being important, or are there any others that you can give to us?
That was to me.
Yes, yeah. Sorry.
Yeah, I agree with what Liam just said. Calibration is really important. Um, uh, a key principle for us, well, we have the advantage of, or I don't know if it's advantage, maybe it's a disadvantage, but we have a lower dimensionality of data than the hyperspectral approach. So we're a point sensor. We're making a measurement at one location and doing exquisitely sensitive measurements there, trying to measure multiple species potentially. Um, and so we like to save all of the spectra. This is sort of the opposite of what David was saying. We don't like to rely just on the process data because then you can never get back to the fundamental measurement if your interpretation is challenged. All you have is sort of the voltmeter output. Trust me. So I understand that it may not always be feasible to do that, but we're a big fan of saving the actual optical signals as well as the derived quantities from those optical signals. And that has done us a lot of good in a few cases, particularly where spectral interferences were determined after the fact, and then the spectra could be reanalyzed to account for that. But it depends on the kind of measurement that you're making. So I'm not saying it should be a universal principle, but it's an important trade-off, whether you save the fundamental signals or not, or at least some of those fundamental signals. That's another thing we do is sometimes just have the user save a spectrum every 10 seconds, just so that you have some record of what was going on at the lowest level of your measurement. I also agree with saving metadata data. We refer to them as housekeeping variables. That's really important. And of course, we take great care to know exactly where we're making the measurement. So everything is geolocated, and we use GPS time servers so that we know when we're making the measurement to within tens of milliseconds. That sort of goes back to a comment, I forget who made it earlier, but it's really typically in a given environmental measurement, our instrument will not be the only instrument there. There will be multiple other instruments. And if you want to look for correlations between those instruments, you really need to be on the same time stamp. And you also need to know exactly where you're measuring, because not all instruments will be precisely co-located. So it's really important to be aware of that, and also to make it easy to transfer your data and have it in a format that you can easily compare all the instruments that are simultaneously making measurements in a given location. And that's not necessarily trivial to implement that in real time. Real time is not always needed, but sometimes it is, particularly if you're doing mobile measurements or something like that, where the uh, area that you decide to sample is in some way determined by what you're seeing in real time. It can be really valuable to have all the instruments feeding into a central control panel, so that the operators can look at the integrated signals and make decisions about how to plan the measurements. Less the case if you're just making continuous measurements all the time. But if you need to direct the experiment in real time, then integrating all the data streams can be really valuable.
Yeah, thanks. And that kind of, you're right. I think that highlights what you were saying earlier, David, about the importance and the need for standardization, so you could compare different systems in that way. But what about from the product side, from a user's evaluation of a product side? How can you be sure about the accuracy of the data that you're receiving?
Yeah, so that there's a few things that certainly we've considered in our equipment, and I've seen, pretty broadly understood in industry. Some of them are as fundamental as built-in tests and validations in electronics themselves. They're as you move from kind of research-oriented basic technology into more commercial grade, prosumer grade type technologies, there's an expectation that at startup that all of the routines and sequences are evaluated, and that you have all of the calibration necessary embedded in the instruments, so that you're not relying on human error, right? That is a big thing to try to reduce, is get humans, which unfortunately are prone to error from time to time, move them out of the loop and allow the hardware, the ones and zeros and the electrons, to do their thing. That becomes a key piece. But the other is to consider secondary signals in the environment you're acquiring in, especially if you do have a broader band measuring capability, as an indicator, right? As a bit of a guide for you. As an example, if you're looking broadly at the visible or near infrared spectrum, you will naturally have some water absorption somewhere in your signal. And if you know consistently that data always is in a certain domain on your sensor, and you see that walk, you don't need a robust calibration routine. You do not need some deep learning algorithm to identify that absorption feature, which is there until the atmosphere no longer exists, has moved. That is certainly an ability to identify that. And I think it's a combination of taking the humans out, but also giving some guidance to humans to assist them along the way.
Yeah, so not just kind of blindly following the data, using your own kind of nous as well. That's great. So moving on now, we've got a question from one of our audience members now. This is kind of one of the bits that I really like to put to you. So, I mean, this will be open out to anyone to jump in and answer. But they ask you to tell give us some information about possible applications in relation to wildfires, forest fires, and sort of protection of cultural heritage locations, maybe in terms of environmental monitoring.
Well, optical methods have certainly been really important to looking at the outflow from wildfires. There are optical methods that are used to look at aerosol composition in the wildfires, and then there are also techniques looking at individual molecular species for tracing wildfires. Hydrogen cyanide and other species can be measured with optical methods. And there's, obviously I've seen several papers recently talking about the impact on the human immune system of being exposed to wildfire smoke. So this is becoming a really important topic as at least in the US, we're encountering more and more wildfire smoke in areas where we never used to have it. I've lived in New England all my life. I don't remember I used to think wildfires were a problem of the West. And now 2 years in a row, we've had smoke from fires in Canada that have been quite noticeable in New York and Boston. So I think it's going to be a growing issue.
Yes, certainly. I have seen a number of technologies applied in the wildfire prevention, identification, and actually post event mitigation and cleanup. Often you'll see kind of the mid-event being a mid-wave or thermal-based camera to better understand sources and whether there's truly extinguishment of the flame themselves. But if you can go ahead of that event and start looking at the moisture content of the trees, of the foliage, of the brush, and identify the most likely source points, areas where you would want to go through controlled burns. I'll even, although it's not an optical technology, I'll just highlight, because it is a outdoor environmental aspect, there are drone companies out there currently working to support controlled burns, where they're bringing via drone capabilities to start controlled burns in remote areas where you don't have to send a human in to take those actions. So I think there's a lot of more broad remote sensing activity and remote action capability there to identify what are the most likely points of ignition, how to identify whether those ignition points are out, and then on the backside to look and understand where did water flow, where did materials flow, where is ash landed, where is there contamination within that ash, identifying asbestos contamination, other harmful chemicals and residues that may remain. Some of the areas that burn are just pure woods, but much of it is actually residential or urban, and that is a significant cause of pollutants. And identifying that and impacts the watershed downstream is critical.
Right, so I mean that covers a lot, the wide spectrum of kind of understanding wildfire spread when they're kind of in action, and also the early stage warnings, but also something that I hadn't thought of, the sort of warnings before they actually begin, based on the environment. That's interesting. Move on to the next question then. So when it comes to optimizing the applications for environmental monitoring, what kind of best practice tips can you share with us in terms of using the components? I'll kind of start off with you, maybe David, as the best person to answer that.
Yeah, I mean, I think there's a couple of best practices, but I'm going to start with maybe the most important one, and it's the one that's often overlooked. People are very enthusiastic about the potential of what can be, and I'd urge you to keep this one sentence in your head, which is before you go try to work something at 50,000 feet, go try to work it at 10 feet, right, or in the lab. Make sure you start simple, because if it does not work in that environment, it will be a challenge when you add the atmosphere, the environment, human interference and influence. And that's a critical piece here. Start simple and work your way up from there. Prove that it's feasible, and don't go for the grand plan. I know it seems like an obvious trick, but it's a very common one that we run into. And the other, I would say, is focus on the workflow as much as the right optical sensor or solution. Think about how the data will be collected, right? It's really an experimental protocol, even if it's a robust industrial deployment. How will I collect the data? How will I download the data? How will I process the data? How will I store it? How will I derive intelligence from it? And how will I make sure that any of the 10 people that work around me achieve the same result? There's a natural tendency to go to the spec sheet and say, what's the perfect number? Really think about the optimum workflow to get the best result. Otherwise, you will have a bunch of data that you don't know how to handle, or the data that you didn't expect to collect.
And Liam, from your side, in terms of your experience, I don't know if you're able to share any of the sort of mistakes that you've made, or kind of changes that you'd like to do differently, or any advice you've got.
I think as Dave and David have hit earlier on, yeah, the outside world is difficult. The temperature, pressure changes. I suppose, and that point is that when whatever measurement you make in the lab, it's going to get worse when you take it out to the field. Also, equally important to figure out exactly why that is the case. So, for example, if you're using a laboratory-based signal analysis, that's often a factor 2 or factor 3 worse when you move to a PCB-based version of the same tool. And I think there's a tendency amongst the photonics experts and photonics researchers to assume the electronics is a solved problem. And yeah, it's not quite. There needs to be a lot of thought given to that problem. Equally, I've encountered a common assumption that as soon as you go for mass producing the electronics, it's going to be cheap. It's not always the case as well, especially for the more specialist functions. So I've seen a number of cases where we've solved the photonics problem, and all of a sudden the PCB, there's a problem with the PCB, or it's not delivering what it's supposed to do. And in terms of how to kind of get around that problem is talking to the end user early, in particular also talking in your the system integrator, to make sure that's planned, even if the system integration is only occurring at the end of the project, or the last quarter of the project. Getting a sensible plan put in place from day one, it just helps alleviate, helps identify the incompatibility, and whether a fiber is going to be 10 centimeters too long or too short, etc. If you can identify, if you get people talking at the earliest possible stage.
Right, thanks. And Dave, are there any kind of from your side? Are there any golden nuggets of kind of advice that you've got that you can leave us with?
Well, I certainly agree with everything that David and Liam just said. In general, when you're making environmental measurements, at least ones that are involve field deployments, not installed monitors that are there all the time, things are just much more difficult. You've got time pressure, you've got varying temperatures. Often you've got people that are working 10 or 12-hour days and maybe are not at their best troubleshooting skills at their fingertips. And you just should expect everything to be harder. And so if you start by practicing in the lab, and then practicing field deployments, do local field deployments near your home base, and we call them shakedowns to see what the problems are going to be once you get out in the real world, because there's just in general, you're trying to get usually 10 different instruments to work perfectly all at the same time in a temperature fluctuating environment with limited electrical power and maybe somewhat dirty electrical power. And that can be a huge challenge. So going slowly, lots of dry runs, and expecting it to be hard, I think is the advice I would give.
Right. So what's the phrase? Failing to prepare is preparing to fail.
Yes, perfect.
And finally, I think we've got time for one more question if I can squeeze it in. So I'll finish by asking you all what kind of changes you think we'll see over the next 5 years in environmental monitoring. They could be changes in legislation, the technology we use, the application of them, or changes in the environment itself, which make the task harder, maybe. I'll stay with you, Dave, there, if you don't mind.
Oh, well, so as we said at the beginning, or maybe before the beginning, smaller and cheaper is always attractive, and there's always going to be pressure to do that. On the other hand, we want accurate measurements, and there are limitations, physical limitations to how accurate you can be if you if you totally optimize cost and size. And so there's a really fundamental trade-off there. Do you want a network of 10,000 instruments measuring noise, or do you want a network of 500 measurements that actually have signals? So that's one area that I think is currently being debated and worked out in the area of environmental sensors. But I think there's also room to grow and to measure new species. And so one of those new species that people are doing a lot of development work for, including us, is the measurement of hydrogen. So with the coming hydrogen economy, we're going to need a lot of measurements of hydrogen to be sure that it's not leaking, both for safety reasons and for environmental reasons. Turns out that hydrogen, although not a direct greenhouse gas, is an indirect greenhouse gas. And therefore, we can't be leaking 5 or 10% of it the way we do at some locations processing natural gas. And optical detectors for hydrogen are very, very difficult. So that's an area of growth. And then finally, the other one I would say, I've sort of mentioned this before, but developing the sampling systems to measure species that are hard to measure just because you can't get access to them. And one of those is in the field of geochemistry, which is not exactly environmental monitoring, but you're monitoring a past environment. So I think it's fair to include it here. There's a push now to use what's called the triple oxygen signal, or the 17O excess in minerals that have oxygen in them, to learn about past hydrology, ecology, and even geography of different environments in the past, and developing mechanisms to go from those minerals to gas phase molecules that can be measured with optical techniques is actually a hot field right now. And there's new science coming out that looks really, really promising. Okay.
And David, in terms of without giving me any kind of sensitive information that you can't give me, what does the future look like from the hyperspectral imaging sort of tool side?
I think what we see and really what's exciting in the coming years is, in general, this integrated multimodal data collection and processing. This idea that we don't have federated sensors, but what we have is a network of multiple sensors that all talk to one another, that give the right answer, not the answer of any individual technology or vendor. As a vendor who makes this technology, that may seem strange, but we all benefit when we get the right answers that people can adopt and use. That is what will drive that acceleration. So that's a piece. Second is really, our business is very heavy into UAV and drone-based data collection, and what we see in global regulation changes around beyond visual line of sight, meaning drones that can operate beyond what the actual controller at the stick can see. That is a huge impediment today to doing wide area collections of the environment. If I want to look at a pipeline or look at a full dynamic large lake field test, I have to be able to maintain constant contact and line of sight to that drone. That limits my ability to operate in an efficient manner and scale my capability. The movement beyond that, and also into unattended acquisition, the fact that I can just have on my farm a charging station that my drone lands in, charges overnight, and in the morning follows a pre-programmed flight plan, and on its own collects data to give that temporal measurement without human intervention. That's another great one, and it wouldn't be a technology session without at least I'll be the guy and use the words AI just for a moment, but I'll say it in this way, which is if we think about what people are doing to build robust algorithms and detection models, the ability to then apply newer tools to make them more flexible, more adaptive, or even self-learning based upon new data structures. These are things that I think are very exciting. Using them in appropriate ways, I think that there's a whole world of capability and automation that we have not even touched at this point.
David, I think you just made the case for saving the raw data.
To be fair, Dave, I'm not opposed to it, but there's places where it's difficult. Absolutely.
I guess that takes, David, what you were saying before about keeping the human in the loop. It kind of goes to advance that process so the humans can be taken out of the loop, as long as we trust the sort of source and its ability to do that, I suppose. And Liam, from your side, what do you think is going to make this tasks like yours easier in the next 5 years future?
I think the idea that once kind of technology or one sensor family is going to dominate is fading, and we're moving increasingly to this multimodal, multi-level network where you have the best in class for each particular task, all being combined, as David was hitting on. And it also appears in terms of pollutants, I think there's going to be we can expect unexpected consequences of some of new green initiatives, with new pollutants being emerging as new fuels and so on are being used. So I think there'll be a few new challenges and new pollutants emerging in the coming years.
Right. Well, I mean, on that slightly scary note, we're just about all we've got time for today's discussion. I'll leave you with that. But once again, you can watch today's discussion back on demand via the Electro-Optics website for the next 12 months. But looking ahead, our next live panel will take place on Wednesday, the 4th of September, where we'll be talking about optical solutions for high-speed data transmission and how we'll meet the demand for faster and more reliable networks. We'll be joined there by Vincent Frasser, Group Vice President of ST Microelectronics, Brad Booth, CEO of LLM Photonics, and David Brinkley, who's the Senior Vice President of Engineering at Tara. Make sure you register early for that to hear how photonics is driving the next generation of global connectivity. But for now, I'd like to thank today's guests again, Liam, Dave, and David, for sharing your expertise and insights with us. So thank you.
Thank you for having us.
Yes, thank you
Thank
for
you.
having us.
Thank you.
Thank you very much.
And goodbye.